Hello and welcome to the Path to Plutus channel. The goal of this channel is to help you along your path to becoming a decentralized applications engineer by first learning a powerful programming language called Haskell and then a subset of Haskell called Plutus, which will allow you to build native smart contracts on the Cardano blockchain should you so wish. This is the third video in a series of videos on specifically learning Haskell, the Haskell part of your path towards Plutus. And in the previous video, we looked at lists within Haskell, how they are basically constructed, how the types that you can put in a list. So if you haven't checked that out, do go and check it because this video builds on top of the work that we did in the previous video, and we'll look at a more advanced topic within lists. So it's important you have a basic understanding of lists within Haskell in the first place before you come along and do this video. And even more so, if you haven't seen any of the videos in the series, please go check out the first video and then come back to this video once you've seen all the videos prior to this one. Additionally, there is also a video on my channel which introduces the channel itself, why functional programming is important and why I'm doing this channel. So please go check it out. Like any videos you enjoy, including this one, do subscribe to the channel and tell as many people about it as possible. It all helps the wider community and as many people as possible to find out about these videos so that they can begin their own path towards Plutus. Okay, so with the housekeeping out the way, we can get started on learning a bit more about lists. And what I want to do is I want to go through something called ranges. Okay, so before we get started on learning about ranges, we need to fire up the GHCI interactive prompt so that we can write Haskell code and have it run on the fly. Okay, so as always, prelude is a good start. It means we've it's all up and running and ready for us to go. So in the last video, we covered, as I said, sort of the very basics of how to construct a list. And an empty list is two square brackets, one open and closing one, and that defines an empty list. And what you can do obviously with lists, as we've shown previously, is you can have lists of numbers. So you can have the list 1, 2, 4, 5, 7, and that will generate that list for you. But sometimes it's a bit onerous to try and define a very long list by hand. For example, the list 1 to 100, you wouldn't want to sit there and type out every single number in that list. You'd hope that there was maybe an easier way of creating that list for you. And in Haskell, there's a really good and easy way. And that is through the use of ranges. So we can say, okay, right, well, I want a list that starts at 1, and I want it to go all the way up to 100. And there you go. So very simply, and with some really nice, concise syntax, we were able to define a numbered list that goes from 1 to 100, and you can define any starting value, any ending value, and Haskell will generate that list for you. But say, for example, you wanted to perhaps instead generate a list of characters that goes from the letter S to the letter Z. Haskell supports that as well. So, excuse me. What it's done is it's gone and inserted into a list all the characters from S right the way up to the character Z. And if you remember from the previous lesson, a list of characters is a string in Haskell. So Haskell has printed this out as one long string. But it's pretty cool anyway that you can use ranges with characters as well. There's another number of interesting use cases for this. which we will potentially go through in this lesson. But if not, it's well documented in the Learn Your Haskell for Great Good, because remember, these videos are based on the content within that book. So if you haven't checked out Learn Your Haskell for Great Good, it's freely available online, and you can also purchase a hard copy for yourself, and I do sincerely recommend that. So, hope I'm not losing my voice here. Right, what you can also do now, when it comes to lists of numbers, we can do some cool things involving steps. So say, for example, you wanted to generate the list again between 1 and 100, but you want to go up by 2 every single time. Okay, so that would require you defining a step. So the basic syntax is roughly the same. The only difference between just defining this list here that goes between 1 and 100, what you do is after the starting value, you add a comma, and then you add the second value. Okay, so what's happened here is we said we want to create a list. The first value is 1, the second value is 3, and then go and create the list up to 100. Right? So what Haskell will do is it will go and it will look at this 3, and it will say, right, okay, what's the difference between 3 and 1? That's 2. So what I need to do is I need to create a step of 2 from 3 onwards. So the next one should be 5, etc. So let's have a look. So here we go. It's created a list of odd numbers 1, 3, 5, 7, 9, 11, 13, etc., etc., etc. And that was really easy to do. And you can again define any number of combinations of lists in this way. It's so much simpler than having to manually type this out by hand. Very, very useful. I really, really like languages that have ranges like this. Not all do, but this is, when I first started learning Haskell, I thought this was a pretty cool feature. That's really simple, and something that you need to bear in mind. You can also go backwards. So what do I mean by that? So say, for example, you wanted a list to start at 20, but you wanted it to go backwards towards maybe the number 1. Now, this won't work. Haskell doesn't really know what to do here. And you just need to give it some extra help. So rather than just saying I want to go from 20 to 1, you have to define the step, right? So you have to say it's going to start with a value of 20. The next value along is going to be 19, and then you need to keep going until 1. So it should be able to work out, okay, the difference between the two is -1. If you do 19 minus 20, that's -1, and then just apply that until you get to the number 1. Right, and then here we go. So it goes 19, 18, 17, etc., etc. So that's really useful. You can do this, use ranges with floats, so floating point numbers, but it doesn't work particularly well. You have some unexpected results, so I wouldn't quite recommend you use it. That's well documented in the Learn Your Haskell for Great Good book. So for a really thorough and great explanation on why that is, do go and check that out. Now, that's sort of almost as far as you can get with ranges. You can't do things like this. So, yeah, it doesn't really like that. But basically, the example here is we have started with a number 1, and then 2, 4, 8. We're basically trying to do powers of 2 here, but Haskell doesn't really know how to do it. It can define one step, but no further than that. So you have to come up with more creative solutions around that. But, nevertheless, they are really useful. Something that is really interesting is the concept of infinite lists. And what do I mean by infinite lists? I mean lists that do this. Right, where you define a starting value and don't define an ending value. And then what you end up doing, I'll stop that because that can get very annoying very quickly, is you can end up creating an infinite list that never stops. And you might be wondering, well, why is that any use? There are a number of uses for that, and I will be covering that mainly in the next lesson. The next lesson will be on the concept of tuples, so it will become more apparent then, and also throughout the whole series on learning Haskell, you'll come to really appreciate why an infinite list is valuable in Haskell. I never quite understood it at the beginning, because something that goes on forever and ever doesn't really make any sense, but there's some nifty features built into the language that make it very useful. But so there's various ways of generating infinite lists, right? That was one way, we're using this syntax, and another way involves visiting the take function. Okay, imagine you wanted to get all the multiples of 13, right? So you start defining a list using ranges. You say the first value is 13, the next value is 26, and so on and so forth, right? But you don't know how many you want, or you're just saying, here are the two values that define that define the multiples of 13. Go away and calculate the rest of the values for me, and say you only want you want to do the 10 times table for 13. So what you want to do is you want to let it generate an infinite list, but you want to say, okay, I want to take from that list, from the front of that list, 10 items, right? So here we go, 13, 26, 39, etc, etc. So until you get 10 times 13, which is 130. So that can end up being very useful, because here I've not have to say go for. What you could do there is, rather than doing take, you could say go up to 130, and it would stop at 130 for you. The reason you might want to use take over this notation is because you might want to define. You might want this value of 10, you might want it to be variable. You might want to have a function that defines this call and then parameterize this part. So depending on maybe the weather or the way your application functions, you are basically then in control of how much you take from this list. You can take as much or as little as you wanted. You can say you can take the first 15. You can take the first 35 if you wanted. Etc, etc. So where maybe you don't know what the end number in this list will be, that might be a useful thing for you to know. It might be really useful for you to use take, because you don't really know what the end number is going to be. So you just say, I want to take 35 values, and then I'll maybe look at the last one, or I'll look at one in the middle. It's all an application specific reason as to why you would use take over just a finite range. Right, so that's a finite range. This takes a certain number of elements from an infinite list, and Haskell won't go along because Haskell's lazy. It won't, because this is an infinite list and it can go on forever and ever. It will never do that because it knows you only want 15 here. It will only ever start at 13 and generate 15 items within that list. It won't go beyond that because Haskell is lazy, and that's a really clever thing for it to do. Rather than saying, okay, I'll generate the list and then I'll pass that list to this function, and this function will take 15 items. No, Haskell only really computes a value when the user wants to see it. So take will, when you execute take, it will try and display a value, and that display value will actually kick in the calculation. So that display will say, actually, I want 15 from this list, and this list in Haskell is not generated yet, so it says, okay, fine, I'll generate the first 15 items in this list. Because remember, as I've said a few times already, Haskell's lazy, and this is what it does very well. It doesn't do any more work than it needs to do. So that's actually a really cool thing to bear in mind when it comes to infinite list generations. Okay, so let's have a look at some other ways of producing infinite lists. So we have the function cycle, and what a cycle does is it takes a list and infinitely repeats it. Okay, so where we had this list, okay, let's just define a new list, right? So we'll say there's a list with the values 4, 8, and 2 in it, and what it will do is it will repeat it, as I said, indefinitely. Okay, I need to stop that. So as you can see, it's just gone, and repeated that forever and ever, right? 482, 482. Okay, that's a lot of numbers. And then what you can do from that is you can use take again to take a specified number of items. So say you wanted the first, say you wanted 20 items from the list that cycle could produce. You say, okay, fine, cycle, go and repeat this list until you end up with a list of 20 items, and then I'll take that away and display it to the user. Okay, so there you go. You have a list of 20 items that have been repeated from the base list 482. And if you don't believe me that is 20 items in the list, you can always use the length function, remember, that will produce the length of the list, right? So there's 20 items in there. Okay, so that's actually really useful. Cycle may come in and may be used quite regularly when you use Haskell. Another thing that you can do is you can use the function repeat, right? Repeat takes a number and then puts it in a list and infinitely repeats it. Okay, so you could have the number 9 and it will put it in an infinite list. It's the same as defining a list using infinite ranges, right? So you start with a starting number of, oh no, actually that's not the same. That's not the same, because what it will do is it will go 9, 10, 11, 12. So ignore me there. So, but repeat will actually, instead of doing that, we'll just infinitely repeat the number 9 in a list. And that's just going to spit loads of numbers on the screen if I print that out. So what I will do is I will take 5 of those items. Okay. Oh. Okay. So basically, I'm saying to Haskell, could you go ahead, repeat the number 9 5 times, and then shove them in a list for me, basically, right? And then it goes away and it does that for me. Now, you might be wondering what this dollar notation is. I'm not sure if I've introduced it yet in this series of videos, so it's worth going through what that dollar notation is. Okay, so take is a function which has 2 inputs, right? It takes 2 arguments. The first argument is the number of items that you want to remove from the front of a list. So this is an integer value. And then the next value, okay, I'm going to highlight this all, is the list. Okay, so it takes two arguments. The first one is the number of items you want to take from a list, and then the next argument is the list in question, the list that you're going to be taking items from. Okay, so because it takes two inputs, you have to be careful about doing function calls, right? So here we don't have, when we call this take, we don't have a list ready. We are generating a list on the fly. So we say take 5 items from a list that doesn't exist yet, right? And then that list is actually the number 9 repeated 5 times, right? This list hasn't been generated yet. And to generate that list, we're doing a function call to this repeat function, passing in the number 9, and it does what I've just said, right? Now, why is that? Why does that matter, right? How is that going to impact on take's ability to take 2 arguments, right? And the way Haskell works is it's left associative. I think that's the right expression. So basically it means that if we didn't have the dollar, this wouldn't work properly. You would get an error. Okay, so what's happening here is, because Haskell's left associative, we have this scenario where take takes 2 arguments, and it thinks that the first argument is the number 5. We want 5 elements from a list, and then it thinks repeat should be a list, and then this 9 is just dangling here somewhere. So it actually thinks that these 2 are the arguments of the function, and then it tries to do what it's supposed to do, and then just completely and utterly fails. So what you can do is you can wrap things in parentheses, okay, to give it the highest precedence. So by giving this function call repeat 9 the highest precedence, we're saying execute this repeat first, repeat the number 9, and then pass that in to the take function as the second parameter. So here now what we've ended up with is the take function. As its first argument, it has the number of items we want to remove from a list, and then the second argument, which we've wrapped in parentheses, is the list from which we're going to take items. Right now, if I run this, the function runs correctly. Okay, so why did I go ahead then previously and write this? Well, this dollar notation is what's called syntactic sugar, if you've not come across that before. So what this does is it adds the parentheses in for us, right? Without us having to do it. Now, you don't have to use the dollar notation, but it actually saves a bit of time, and it's just easier as you're writing this call to just shove a dollar in there and say, do you know what, everything after this dollar is going to be wrapped in parentheses. But we're not going to explicitly do that, and this is just going to be syntactic sugar. So now when you run it again, it runs successfully because you've given it 1, 2 arguments. Yeah, and I know I've repeated myself quite a lot about the arguments to this function, but it's important that you understand how this works, and this is used very commonly in Haskell to try and avoid. You basically are trying to avoid situations where you end up with lots of parentheses around things. You can end up with, in here, you could really end up with another function call to get your value. So, you might have get value, and then that returns something. But in there, you might want to pass another function. And you can see how the parentheses actually build up quite a bit. So, and that's without, having to add another one around repeat, right? And then doing another one which does another function call. So it's just reducing the number of parentheses and precedents that you have to apply. So that's why the dollar notation is used. So if you've been reading Haskell code and you don't know really what that is, then you do now. It's used slightly differently in Plutus, but we won't worry about that for now. Okay, so we've looked at cycle, we've looked at repeat. An easier version of repeat is the function replicate. So replicate, no. Okay, so replicate. Let's have a look at, it's supposed to just repeat an element and produce a list of a fixed size. So yes, I remember this now. So you have, okay. Yeah. So I just forgot to supply one argument to this function, right? So here what I'm saying is I want to repeat the number 7 6 times, and I want you to put it in a list. So rather than using the repeat function and then taking stuff from that using the take function, we just say replicate this number X number of times, right? So in this case, replicate 7 6 times. So that's actually quite useful and saves you having to use take if you prefer that. So that concludes the first part of this video, which is looking at ranges. And now what I want to do is I want to go and look at list comprehensions as another way of generating lists. But before I do that, I just want to cover something called set comprehensions. And you might have come across set comprehensions in mathematics. You might not. It's not a problem. I'm going to go through them now to basically help you understand list comprehensions in Haskell. So really don't be put off by this. This is actually really easy. So what we're going to do here is we're going to start. So this set comprehensions are a way of defining lists of numbers, a list of unique numbers. So that's essentially what sets are, unique things. So this is the notation, the mathematical notation for doing that. What we're going to do to start with is we're going to focus on everything to the right side of the red line. Okay, so let's start at this bit here first. Okay, number 1, right? So what this says is that we want to look at all the numbers that are natural, right? All the positive integers from 1 to infinity. It sometimes starts at 0, but we'll just say for now that it starts at 1 and goes to infinity. So here we're just saying x is a natural number. It's part of the set of natural numbers from 1 to infinity. Okay, so imagine creating basically a range, an infinite range, starting from 1 and going upwards, right? It's essentially what it's saying. Okay, so then the next important thing is this bit over here, this predicate. So what it does is it reduces the list of possible values that we're going to look at in this set, right? So this predicate says let's restrict the set of numbers to anything less than 10. So now we've gone from a list, a potentially infinite list from 1 to infinity, to basically a list between 1 and 10. It's quite simple. And then what we want to do for every value of x in that list, right? So 1, 2, 3, for every single value, we go over to the left side of this bar here and we multiply them all by 2. Okay, so we're saying we're going to take this number 1, we're going to multiply it by 2 and get 2, multiply this second one by 2, and we're going to get 4, we're going to get 6, 8, etc. So that's set comprehensions. That's quite easy to understand, and I think it's even nicer to understand in Haskell. So this is Haskell's list comprehensions. Okay, so all right, start here at number 1. Right, so we create a list. So what we're trying to do here is replicate this set notation in Haskell. This exact same example. Right, so we start with the list of natural numbers from 1 to 10, as I was doing it in the interactive prompt. So we start with a list of natural numbers from 1 to 10, and then some new magic happens in Haskell. We have this new syntax, this left arrow, so left and a dash, and basically we have this concept in Haskell called drawing down from a list, right? So this says draw every single item from the list here, one item at a time, and store it in X, right? Draw each element out of the list and store it in X. That's quite important, because then the magic, any manipulation on X happens on the left, right? And in this case, we're multiplying X by 2. So every single X by 2, and after each multiplication, we put that into a new list, and we end up with a resulting list. So let's have a look at how that would look like when we actually ran it in Haskell. Okay, so we have every single X from the original list multiplied by 2. So remember, we had the starting list of the natural numbers from 1 to 10, and then we used list comprehensions in Haskell to extract or draw every item from the list, store it in X, multiply it by 2, and then one by one add it into a new list. So we started with this list, and everything is multiplied by 2. That's really, really handy. And the notation for that, if you can appreciate it, is so concise and so easy to understand. You just have to read things right to left. So again, you have a list 1 to 10, draw everything down, put each item one by one into X, and then you hop over on the left side and you multiply everything by 2. And that's really nice. However, you might encounter scenarios where you want to draw down from a list, but you don't necessarily want to manipulate every single item in a list. So what do I mean by that? Well, let me show you this example. Okay. So, everything is largely the same. Everything that I'm highlighting there is largely the same, except we've introduced something after a comma. Right? So what this is on the right is a predicate. And I don't think I explained necessarily what the definition of a predicate is. If you've not heard of it before, the term, a predicate is an expression that results in a true or false value. It's just basically, a truth statement, right? So this predicate, right, what it does, is for every value of X that has been drawn from the list, it multiplies it by 2 and then checks if that value is greater than or equal to 12. Now, not every item in this list is going to satisfy this predicate, i.e. is going to result in true when run through that expression. Okay, so what we end up with versus the first list comprehension is we end up with a much larger list. So here, this is doing, so let's go back and to avoid confusion, let's look at the current example with the predicate. So here, what we end up with is a list where X multiplied by 2 is greater than or equal to 12. And that's right, so we have 12, 14, 16, 18, 20. So that's done exactly what we wanted it to do. So it's reduced down the list. And every single value of X in a list has to satisfy the predicate. It has to be true for it to even come to this side of the bar and include it in the list. If this predicate is false for any value of x, it won't be included in the list, as you have seen. So that can be very useful. And you know, you can, let's just let me just double check something. So the thing about predicates is you can have as many of them as you want, but the value of x has to satisfy every single predicate for it to be included in the list, right? So we have this example here, which has more than one predicate. So we're drawing down from a single list, but we're applying every single value of x to 3 predicates, right? So we're saying for the list between 10 and 20, I don't want x to be 13. I don't want you to include or do any manipulation of x. We're not doing any manipulation here, but you might be doing a manipulation. But in this case, it's just a filter. So we're saying, take this list and filter it down and ensure that there is no value of 13 in the list, 15 is not in the list, and 19 is not in that list, right? And if you check here, neither of those values are in the list because it didn't satisfy that predicate. And remember from the first video, not equal to is done like this in Haskell, / equals, right? So if we wanted to change that, we can say it needs to be double equals. Actually, I want you to filter down the list and include the values 13, 15, and 19, and x is equal to 13, x is equal to... Not sure why that didn't work. I'll have to look into it and come back and you know, maybe add it to the description as to find out why that hasn't worked. If you guys can figure out maybe why that doesn't work, that would be great. Yeah, that's a bit baffling. We should have ended up with a list that only included 13, 15, and 19. Not sure why, but you know, I hadn't planned to do that example, and that's what happens when you try and do examples that you've not planned and tested yourself. Anyway, I've got more list comprehension examples that do work, and they involve things. They involve if statements. So we have introduced the concept of if statements in previous videos, but let's revisit them and actually apply them to list comprehensions. So what we're going to do here, right, okay, let me just, because I've copied and pasted this, the characters are not very GHCI friendly, so I need to replace the quotation characters because this is going to complain. Okay, right, okay, so what we've got here is a function called grade, right? And what it does is it takes a parameter called skill levels, and then we have the function definition here after this equal sign, okay? And the function definition is the result of a list comprehension, okay? So we have this list comprehension. So let's start on the right side of the bar. Okay, so what we do is we have, so we look at this skill levels list that has been passed in, and we draw using the left arrow. You can't see it because it's over 2 lines, so apologies about that. But we draw one item at a time from the skill levels. It's just going to be an integer list, which will have the skill levels of some students on the course, some random students. So it will draw one item at a time from this list and put it in skill. Okay, and then we can do stuff with skill to the left side of the bar in this list comprehension. So we're saying here, if skill is greater than 100, then you're a Haskell Pro. Otherwise, else, and you always need the else clause of an if statement in Haskell, because if statements are expressions, which means that they produce a value. Java is not like this. Kotlin is, it will produce a value because it's an expression, right? So, but anyway, that's you just need to make sure that you always include the else clause, because you have to return a value out of an if list. An if statement. If lists are not a thing. Right, so if the skill level is greater than 100, then you are a Haskell Pro, otherwise you need P2P. So this is a function definition, right? And if you have forgotten how to define functions or want to revisit how to do that, that's the first video in the series. Additionally, you can always flick through the Learn Your Haskell for Great Good book, and it will go through that for you. So let's define that function. Okay, so that's happy. I've not had any errors like I did previously. And what we need to do is we need to define a list called skill levels for students. Now I'm just calling it a different name because I don't want you to get confused between the parameter name of this function and a list I'm creating outside of the function. So what I'm going to do is I'm going to use ranges. And I'm going to just define a short list between 95 and 105. Right, okay, so that will just have different skill levels of the students on this course, and we can then supply it to the grade. We can grade the students, and it will tell me, who needs the path to Plutus channel and who is a Haskell Pro. Okay, so all you do is you type the name of the function, and then you pass in your list. If I don't do that, it will say, well, I expected something, so you need to supply something. So skill level, hang on a second, skill levels students. Okay, so that's gone in and produced a list for us using list comprehension. So because the list went from 95 to 100, it's going to, up until it gets to 100, it's going to say you need part of Plutus, and then it's going to say the rest are Haskell Pros. And it's really basic. It's a really crude function. It isn't really, it's not really any use to anybody, but you get the gist of how you can use conditional statements within list comprehensions in a really concise manner. What I've done though is I've also defined a variation of grade, okay, and in this example, okay, the difference between the previous grade function and this one is firstly the name of the function. So I've appended an apostrophe, and this is a really common notation in Haskell. When you want to define different variations on functions, you might see the apostrophe. So the basic name used, but added an apostrophe. That's a valid name in Haskell, and it just allows you to, rather than thinking of a whole new name for a function, which basically does the same thing, but is not the old function, then you use an apostrophe. And it still takes a list called skill levels. It still prints out you're a Haskell Pro if your skill is greater than 100, or you need path to Plutus. And it still draws from that skill level list and puts it in skill. But the difference is we've added a predicate here. So we've just said if the skill is an odd number, then we are interested in it. If it satisfies that predicate, then we will proceed with this left side of the list comprehension. So if I instead call grade, but with an apostrophe on the same list, I should get a shorter list. So here we have three people that need the path to Plutus, and 3 people that are Haskell Pros. So you can see how now it's really easy to define list comprehensions. the notation is a bit scary, maybe potentially for somebody new to Haskell, but I hope I've broken it down really in an an easy to understand manner. And we can so previously I've shown you how to in list comprehensions I've shown you how to obviously draw from a single list, how to use predicate in a list comprehension to filter down the list before we do any manipulation and before we add any new items to a new list. But what I've not shown you is that you can, just like you can use multiple predicates in a list, you can also draw from multiple lists. So say for example we wanted to write our own seed generator for a cryptocurrency wallet. And this seed generator only produces 3 words. Okay, so what we're going to do is we're going to produce those 3 words for every seed from 3 lists. So the first list is going to be this one. Okay, and then so that's gone and stored it in the ones list. We have a twos list. Then 3s. Okay, so what we're going to do is we're going to use these 3 lists to generate seeds, and you will see how in a second, because what we need to do is we need a function that's going to do that for us, right? Or it doesn't have to be a function, but we need to use list comprehensions, right? So let's stop that. Okay. So here we've defined a list comprehension, okay? On the right side of the bar, we have 3 drawdowns from 3 lists. So for this first list, we're drawing every item from that list and putting it in 1. We're drawing every item from the 2s list, putting it in 2, drawing every item from the 3 list and putting it in 3. And what happens when you draw from multiple lists is you get every combination of every list, okay? And you'll see what that means in a minute. But basically, once we've drawn from every list, we then concatenate this string from 1 with a space, and then we add 2, and then we concatenate it with another space and add 3. And the result is this, right? So what I mean by every single combination of lists is that it will start with the first list and draw its first element. And in the first list, we have IOHK as the first element. So IOHK will get drawn from the ones list, and it will get put into 1. And then it will draw from the twos list, right, and store it in 2, and from the 3 list and put Cardano in 3. But what I mean by every single combination of lists, so basically from the first draw, from IOHK being drawn into 1, we then draw down every single combination of the other lists. So we start off with IOHK as the first element, and then we draw as much as possible from the other 2 lists. And when we've exhausted the other 2 lists, then we come back and draw from Plutus and exhaust the other lists. So you can see here from the output that the first word in the seed here is IOHK, first word in the seed here is IOHK, right? But if you look here, first 2 words are the same, but the third word is changing, right? And then the second word changes, but IOHK is still saying the same, right? So IOHK is the first word in the seed until we get to this. Plutus then becomes the first word in the seed. And then we draw down from all the lists until we've exhausted all the combinations where Plutus is the first word in the list. And then Marlow is the first word in the list, and then we draw down from the other 2 lists. And you basically get all sorts of combinations, and this can take place for numbers, etc. So Might be a bit tricky to wrap your head around, but have a play around with this yourself. Try do it yourself and try and understand what I'm trying to say about you get every single combination of each list. If I've not explained it well enough, do have a look at, again, the Learn Your Haskell for Great Good book, or try and check out some other examples online. This is probably a tricky thing that I struggle to get my head around, but you might not. You may understand really what the gist of it is, but it allows you to do some interesting things from that. Okay, so one final thing that I want to do with list comprehensions before we end this video is I want to try and define our own version of the length function, right? So the length function is used on lists to tell you how many items are in a list. So in this list, we have 3 items in this list, but let's define our own, okay? Let's use the apostrophe syntax to create our own version of length, right? So we've this is our own version, and what it does is it takes a list and it's going to produce an integer, right? So lists in Haskell are often referred to as x's, mainly because then when you draw every item from a list, that item becomes an x, basically. But lists in Haskell are referred to as x's. You'll see in many examples online. So what we want to do is we want to define our own function that gives us a length of a list, and we're going to do it like this, right? Watch this. Okay. Okay, so what we have here, if you haven't worked it out already, is we have a list comprehension, and it's going to draw down items from this list, this x's list, and it's going to store it in this underscore. Now, if you've not come across underscore notation before, it just basically means that we are doing something to the list, but we don't care about the values of the elements within the list. So we're drawing elements one at a time from this x's list, and we're putting it in this underscore, but we don't actually care about what that value is. And the reason is because when we come to this left side of the bar, what we're doing is we're just simply pushing for every single item in that list, every single element, we're pushing the number 1 to that list. So you end up, for a given list, you end up with, if you just look at the comprehension, we just end up with a list with lots of 1s in it. And then that list, the resulting list, gets passed to sum, and sum goes along and sums up every number in the list. So because you only have 1s in a list, it goes and adds that all up, and you get the length of a list. So let's try and use that ourselves. So we have length, and if we supply it 893, we get the number 3. So that's quite interesting, and when I first saw this, I thought, oh right, that's, it's really cool that you can define your own versions of language functions in a really concise way, and that that has been the theme throughout this video is how concise the syntax is. You'll find in general Haskell is very concise. It does have its mathematical aspects to it visually, and that's why it works very well in academic contexts. But you don't have to be a mathematical genius to be able to pick up Haskell. It's really straightforward and easy to understand. So I hope this has been very valuable, and you've enjoyed the video and learnt a lot. Do please like the video if you enjoyed it, subscribe to the channel, also share the video out. Like I said in the video, we're going to be looking next at tuples as a way of defining new types in Haskell, and we're going to look more broadly at the type system within Haskell. Haskell's type system is very powerful, very broad, and it's good to have a good understanding on how that works. So thanks again for watching. I will see you next time.